Good afternoon, everyone, or good morning, or good evening. Depends where you are in this beautiful world of ours. Brett Zerba here, Taco Tuesday, Commercial Focus. Good afternoon, Mr. Jeff Maddox. Haven't seen you in a while. Hopefully, we do get to see you soon. So it does appear that we're being heard and seen worldwide. If anyone else wants to say hi or raise their hand, so we know, that's fine with me. Um, uh, so no problem there. Hold on a second. I just messed up. I messed up.
How
You
did
know,
you
you,
mess up, Brett?
yeah, I know it's unbelievable. Anyways, welcome to today's webinar put on by the commercial training team. Today's main presenter is going to be Tony first, Baton Rouge. Hey, Henry, Baton Rouge, Louisiana. I like that spot. I got to visit that. That's a nice area. Nice area. Big school down there. I wonder what school it is. Almost season, almost the time for season down there. Anyways, there is a handout. Today's slides are available, so you can download them from the site if you'd like. I think most of you know history of Takeo, but we are a 105-plus-year-old company, privately held, third generation. And Fairbanks is checking in. Two folks from Fairbanks, Tim and Paul. Oh my God. I guess that is morning over there. It's either 3 or 4 hours, at least 4 hours, I think. In Sacramento, a lot of early birds today, a lot of early birds. Anyways, today's presentation is going to, excuse me, on variable flow chilled water systems. An interesting topic, to say the least. And I do know this, because the word water is in it, a lot of green products can be used on almost every design, Think about that. And green, that's a nice color, very nice color. I have some green in my pocket. So, anyways, I digress. I just came off. I took a few days off. I went to a spa and did a water journey yesterday. So I'm a little, I'm just getting back into the swing of things. So I'm a little more goofy than normal today. But anyways, I'm glad you all joined us. Hopefully you get something out of it, and I'll be monitoring the questions. So ask the questions. Tony will be going through his slides very, very shortly, and stuff like that. We have a class, an in-person class coming up. So if you ever want to come see Takeo headquarters in Cranston, Rhode Island, and our welded products division in Fall River, Mass, get a hold of your Takeo rep. They have opportunities throughout the year. At different times. Every rep does bring people in. We like to have it with the rep when they come in, so just keep that in mind. It's something to consider, and you can get more information from your Takeo rep on that as well. But the classes, they fill right up. We have a big classroom, and that classroom is pretty full, and so keep that in mind. Anyways, again, privately held company, third generation. Johnny White is the Johnny White Jr. is the current leader of the troop, and his global CEO is Cheryl Merchant, and Cheryl and her team have done a fantastic job growing the company. Our expansions is unbelievable. And I know this is the 50th year celebration of the movie Jaws, believe it or not, a couple weeks ago, a month ago, whatever it was. And I remember one scene in that movie, you may need a bigger boat. Well, even with some of our expansions, we may need a bigger building. I'm already hearing in some regards. So thank you to all you folks out there that help us make that all positives. So anyways, I think I'm done yapping, Tony. I'm going to turn it over to you. And please ask questions. I have learned quite a bit from Tony over the years. Tony and I have quite the history, believe it or not. I've gone sailing with him in Newport, Rhode Island, a long time ago, for goodness sakes. Excuse me.
Yes, you have.
But anyways, we are so happy to have him on staff, and he's very, very knowledgeable in our industry. And I bet you, if you try to zing him with a question, he'll know the answer, and he'll get it right. So, anyways, Tony, take it away. I'm done. I'll be watching for questions, my friend. Go ahead.
All right, Brett, thank you very much. Good afternoon, everybody.
Tony?
Yes, sir. Can you hear me?
Can't hear you, Tony.
Hang on a second.
Oh, boy. You were hearing, I heard you before, but is anyone, oh, you can hear him? Okay, never mind. Ryan can hear you. So go
Okay.
ahead, Tony.
All right. So good afternoon, everybody. Welcome to another Takeo Tuesday. Brett, thank you very much for the wonderful introduction. And yes, we have known each other for a very long time. And I had hair, I think, when I first met you. Not much of it, but a little more than I have now. Anyway, we're going to talk today about variable flow chilled water systems and what they really mean and what's different, where's the industry going and all that. So we're going to kind of talk about where the industry is going. We're going to talk about the evolution of systems, how they've changed over the years. We're going to talk a little bit about the reality of what happens in primary, secondary chilled water systems. Talk about some design ideas, things like that. We're going to talk a little bit about heat rejection, because at the end of the day, we can't talk about a variable flow chilled water system if we don't talk about variable flow heat rejection and what can happen on that side of the equation. Because we can take all the heat out of the building, but I got to get rid of it. And so I got to understand what's happening on both sides of the equation. And then the last thing we're going to talk about is a real life example of what can go wrong when you have a system and you don't pay attention to the little details, the little gotchas that happen within a design. So with that, let's get started. From a design perspective, I worked as a design engineer for a number of years before I came to Takeo. And so where do you start? What is engineering? It's not just selecting equipment and putting lines on a paper. There's a lot that goes into it. And it's not just one person working on it. Designs involve a team, and it's sitting down as a team and talking about things and talking about what the owner's project requirements are and how you're going to get there, and throwing all kinds of ideas out there and throwing them up on a whiteboard and everybody talking about it, figure out what's good, what's bad, to eventually develop a final design concept of what you're going to design. It's not as simple and straightforward as just sitting down in front of a blank sheet of paper and throwing lines on it. There's a lot more involved in it, okay? And it also involves your various reps, your chiller reps, your pump reps, reaching out to the Takeo guys and get us to help you. That's what we're here for. We're here to help you make your designs better. So we look at things, where's the industry going? Well, at the end of the day, ASHRAE's provided lots and lots of guidance, and the industry guidance is towards a net zero building. The guideline is to use less energy, okay? And at the end of the day, if I look at all the different design guides out there, the guide is to use less energy and move towards a zero energy design concept, okay? Because we want to reduce energy consumption. At the end of the day, our net goal when we design any system is to use less energy every time we design the building, okay? And so newer systems, we've moved towards less energy consumption, okay? Now, if we look at what we've got out there today, generally speaking, ASHRAE 90.1 is the standard, and that's what's required by code, okay? Understand that code is the absolute minimum, okay? So while ASHRAE 90.1 does reduce energy consumption, it is the ASHRAE 90.1 design is a combination of fixed and variable speed flow control. So it's fixed speed or fixed volume on the primary side and variable speed on the secondary side. And they also define a 15-degree delta T on the secondary side, not on the primary side. As we move into other design guides, either the green guide or the ASHRAE Advanced Energy Design Guides, what we're doing is we're moving away from primary, secondary, and moving towards variable primary. And if we really want to maximize our energy reduction, we want to do variable primary with demand control pressure reset on our pump control. And that's a whole nother discussion that we're not going to really touch on today. That gets into a much deeper analysis of chilled water systems. But what we really want to do is be able to model our system and model our building to determine what the energy reductions are really going to be. Okay, so that's kind of where the engineering side of this is going. So when I look at this, what's the piping look like? Because it's really all about the piping and understanding the different piping scenarios that we have out there today. So years ago, way back when I started out, probably you too, Brett, is we had constant primaries. We had three-way valves on all the air handlers and constant speed pumps and constant speed chillers, and that's what we did. Well, the reality is those are gone. While if the system worked, it was an energy pig. So we don't want to think about designing constant primaries anymore. Okay. Then we migrated to primary secondary. And the first iterations of primary secondary were three-way valves, and we had constant speed on both sides of the equation. While that was okay, it worked, it did what it needed to do, but it was really difficult to save energy. So we kind of changed away from that and went to a constant primary with a variable secondary. And the variable secondary, we still had to deal with things like minimum flow. We had to have, because you can't slow a pump down to zero. There's a minimum speed you have to maintain. And there's still problems with this, okay? And what we have to understand is we got to understand the problems that happen with a constant primary and a variable secondary, okay? Because there are some real serious issues, and we're going to talk about that here in a couple minutes. The better iteration of that, where we still have primary secondary, is an all variable primary and an all variable secondary. So we have variable speeds on both sides of the equation. That works. That is a better alternative. However, if you really want to drive your energy consumption to the lowest possible denominator, what you really want to do is go to an all variable primary. So that way you don't have secondary pumps, you only have primary pumps, and it's all variable speed. You have two-way valves everywhere. And one thing you'll notice when you look at this is that valve in the middle that doesn't have a coil associated with it, that one right there. What that is that is a minimum flow control valve. And we're going to talk about that because that's a really important piece to understanding all variable system, especially with variable primary. Okay, so we've done primary secondary, and in a conventional constant speed primary, variable speed secondary, there are some problems, and there's some problems that we all need to understand and we need to deal with, because they will impact the energy side, and they will impact the performance of your plant. Okay, so on a design day, and we all know that the design day is less than 5% of the operation of the system is at design conditions. Okay, so if I have a 1,500 ton system, 3 500-ton chillers, 3,000 GPM on the primary, 3,000 GPM on the secondary, 12-degree delta T, everybody is happy because I'm moving the same amount of water on the primary as I am on the secondary. And there's zero flow going through the hydraulic decoupler. And in that condition, everybody's happy. Because one thing we got to remember is what happens to my chiller efficiency as I decrease the delta T. My chiller efficiency goes down as I decrease my delta T, because what's happening is, as I'm decreasing the delta T, I'm increasing the lift across the compressor. Okay, so because the return water temperature is coming down, and in that condition, as that compressor lift gets higher, the energy consumption stays up. Okay, so that's why this is an issue. So if I look at this, now let's look at a reduced load condition. Okay, I've only got 1,125 tons of load on the system. My chillers are only producing 375 tons. I've got 2,250 GPM out on the secondary, and I've got a 12-degree there, 12-degree delta T, because the air handlers are doing what they're supposed to do, and I've got the right water flow out there. However, on the primary side, because I've still got all three chillers running, and it's a constant primary, I'm moving 3,000 GPM, which means that I've got 750 GPM going through my hydraulic decoupler. And what that means is because I'm taking supply water that's coming right off the chillers and bypassing it right around to the return side, my chilled water delta T is dropped. On the chiller, on the production side, now I've only got a 9-degree delta T on the production side, even though I've got a 12-degree delta T in the building, because of the mixing that is taking place and because of that water that's going through the bypass. Okay, this is the reality to a constant primary, variable speed secondary. So we've created a low delta T syndrome right here, just by the nature of the design. And it doesn't get any better as I reduce plant load. Okay, I've still got water going through the bypass. In this case, now I'm down to 500 GPM, okay, because I've staged some pumps off and I've staged a chiller off, but I've still got more flow on the primary side than I do on the secondary side. And as you notice, now at 25% load, I'm down to 1 chiller, but I've still got water going through the bypass. So I'm losing chiller efficiency as I decrease my capacity, okay? So how do we deal with low delta T? Well, there's lots of causes for low delta T in the system, okay? First of all, if I got dirty coils in the air handlers, improper selection of 2-way valves or 3-way valves, understanding valve authority, not just pressure drop. You can have piping issues. We can also look at, adjusting chiller delta T's. We can overpump the chillers. There's lots of things that we can do. Ideally, what you really want is variable speed chillers, because that's the best thing that you can do to get out of this condition, because now you can match your chiller load to your building load a lot closer, but that involves having to have variable speed pumping on both sides of the equation. At the end of the day, what we have to understand is I have to solve low delta T problems out on the load side, but I have to mitigate them at the plant level, okay? So if my design leads itself to creating a low delta T problem, that's a plant level issue. Whereas if I've got other issues out in the system, I've got to fix the system issues so that they don't negatively impact the plant. So it's an understanding of both sides of the equation. So when I look at a variable flow plant, things I have to take into consideration. I really got to understand the control side of the equation. And the way we've controlled chillers for years and years and years is we had feedback control. And that's the way we've done temperature control of all kinds of things. That's how your thermostat at home works. That's how we've controlled discharge air temperature and mixed air temperature and boiler controls, and all that have all been on feedback control. We have a set point and we wait until the control variable changes against set point before we do anything. So we're sitting there watching chilled water supply temperature, and the chilled water supply temperature rises and we stage up the chiller. That's what feedback control is. It's a wait and see. And while it works, it's not energy efficient and it's slow, and you can actually lose control of the building depending on how it's set up. If I tune my control loops out for a given load condition, when it's either warmer or cooler than that given load condition, then what's going to happen is I'm not going to be as reactive as I need to be, because it's not a dynamic condition. The setup and the PID values are all a static, based on however it was the day that they tuned the control loops out. Okay, what we really want to look at is moving into a feed forward control scheme. Okay, and what feed forward means that I'm going to look at multiple parameters. Okay, I'm going to look at chilled water return temperature. I'm going to look at chilled water supply temperature. I'm going to look at differential pressure or pump speed or flow rate. And as the flow rate moves up and down, as the chilled water return temperature is moving up and down, and I'm watching what the load is doing in the building, I'm automatically adjusting my control gains. So I'm constantly adjusting my proportional integral values as the load on the building changes. And by doing this, this is called feed-forward control, and I'm intelligently looking at how I'm controlling my plant and how I'm controlling my chillers to maximize the energy reduction and make the system that much more energy efficient. And most everybody's building automation system out there on the market today, all the guys that do this on a regular basis, and I won't name names, but you guys all know who they are, they all have the capability of doing this. But it's up to us as design engineers to make sure that we specify, look, we want feed-forward controls because we want to maximize the energy efficiency and reduce the energy consumption to its lowest possible denominator. Okay. So what are the things we got to look at when we look at a variable flow system? What's important? What do we have to consider in looking at that system? Well, so we've got, all kinds of different chillers out there. We've got air cooled, we've got water cooled, we've got scrolls, screws, centrifugals. There are a myriad number of chiller types. Chiller type is not the important part. Okay. First thing we have to understand is the chiller controls must be able to compensate for a change in flow. So the chiller controls themselves, what comes on the chiller, has to be able to handle that variable flow rate. Okay, they need to be able to react to that flow rate. Okay, the chillers have to have adequate flow turn down on the evaporator side. Okay, and we're going to talk about turn down here in a minute, what that really means. But the chiller has to have adequate flow turn down. Okay, every chiller on the market, and I don't care whose it is, has a minimum and maximum flow rate for the evaporator and for the condenser. Those numbers, the minimum and maximum, are carved in stone. Every chiller manufacturer sets them based on what they know, the tube limits, control limits, everything else about the machine. They set those limits. You cannot go above or below those. If I go below them on the evaporator side, I'm liable to freeze up the chiller and turn it into a block of ice, which gets really, really expensive to fix when you bust tubes. And if I exceed the flow limits and I have too much flow going through the tubes, okay, high velocity will erode the tube surfaces. Okay, so you have to understand there are flow limits there and they're there for a reason. Gotta live with those. Understand that if I have a variable flow chiller and I have low flow and I get down to that minimum, my chiller efficiency goes up. I end up with an extremely efficient chiller. Okay, so understand that having a variable speed chiller is really a good thing. Okay, because you get much better energy performance out of it. So when I look at this, in the world of chillers today, we have two different types of evaporators. Depends on who the chiller manufacturer is. It also depends on the size. Okay, generally for water-cooled machines in screws and centrifugals, generally it's a shell and tube evaporator. And this is what the standard has been for years and years and years. And with a shell and tube evaporator, the chiller manufacturers do things to the chiller, to the tubes, to enhance surface area. And some of the things they do is they can internally rifle the tubes, they can internally thin the tubes, they can externally thin the tubes. There's all kinds of things. Basically, they cut grooves on the outside of it. Rifling is what you have, is the twist that you have normally like in a shotgun barrel. You have a rifling to it, or a rifle barrel, I should say, not a shotgun. So that rifling helps get the water turbulent inside going through the tubes. In a brazed plate, that's real common especially in the package air-cooled market, in air-cooled scrolls and screws. We're seeing a lot of the brazed plate heat exchangers. They're smaller, more compact. And because of the nature of how that brazed plate is built, it's built just like a large plate and frame heat exchanger, except it's in a brazed configuration. So you don't have gaskets in between the plates. That corrugations that are in the channels create turbulence. And so you get lots and lots of turbulence in there. Turbulence inside an evaporator, inside a condenser are good things, okay? But understand the chiller manufacturer is making all those decisions about what you have to, what kind you have. But understand you got different types, okay? And they both have their pluses and minuses. I'm not saying one's better than the other. So when we look at chiller evaporator turndown, this is really critical to understand. Chiller turndown is nothing more than the flow, the minimum flow, divided by the design flow. That's all it is. It's that simple. That's the turndown percentage. So if I look at this, my chiller turndown, so let's say this particular chiller has a 600 GPM minimum flow and a 1000 GPM design flow. That means that chiller has a 60% turndown. That's a really good selection. That gives me lots of rangeability for what that chiller can do, okay? So the other thing we have to consider when I look at my system, I have to think about system volume. And the reason this is important is, we've gone to two-way valves. So we don't typically have three-way valves out in the building. And in a variable primary system, where I've got variable flow through the chillers, I have to think about the volume of water in that chilled water system at that minimum flow condition, okay? And you got to think about this in any chilled water system, but it's really, really critical on variable flow, okay? So in any chilled water system, I have to have 3 gallons of system volume for every ton of refrigeration capacity. Okay, that's for normal air conditioning. If you move over into the process world, we want 6 to 10 gallons per nominal ton of chiller or refrigeration capacity. Now, by the way, these are not my numbers. These are not TACO numbers. These came from Trane, Carrier, York, JCI, Daikin, all of the chiller manufacturers. All of them have the same volume requirements, okay? And if you need a volume tank, we can definitely help you with that because we make them over in Fall River. But understand that this is a requirement. So if I have a minimum flow condition and I don't have three-way valves and I've got a minimum flow bypass valve in my chiller plant, my minimum volume is what's in the plant, okay? So even though I may have enough volume if I got it out in the system, if it's only in the plant, I may not have enough volume because it's just the water in the plant. So I got to think about that. Think about how much volume is right there. This is one of the reasons that three-way valves out in the system, a few of them, to maintain the minimum flow is actually a good thing. But because then I get to account for all that volume. So things to think about. So if I look at variable primary flow, things you got to understand. Chillers have to have equal pressure drop, and I've got isolation valves on each chiller so that when I'm not using that chiller, it's isolated off, so I don't have flow through that chiller when it's not running, okay? So that's one of the critical pieces. I also have this minimum flow bypass valve, and I have to maintain minimum flow. Minimum flow is based on the minimum load of a single chiller, okay? So it's the minimum flow required at the minimum load for that chiller, okay? That's the important part. And that's what that valve's got to be sized for, okay? So normally in primary, secondary, we've preached for years and years and years that there's no bypass, there's no valves in the bypass. And a variable primary, guess what? We're putting valves in the bypass. And so we've got to maintain, one of the things that you have to understand with a variable primary system, chillers have to be equal sized. This is not like a conventional primary secondary where I've got a constant speed primary where I can have unequal sized chillers. Variable primary, they're all gonna be the same size because they have the same pressure drop. And the other thing is you want to manifold your pumps. Don't dedicate your pumps to each machine. You want to manifold them on both the evaporator side and the condenser side, okay? And how you control the pump, whether you're doing self-sensing, whether you're doing DP control, or you're doing critical zone reset on pump speed, there's lots of ways to control it, but you want it controlled based on what's going on out in the building, okay? You will get lower pump energy because one, you got rid of half the pumps, okay? Got rid of all my secondaries. and you're also going to lower installation costs and everything else. So there's lots of reasons to do this. But what you've got to understand with this is the chillers have to have adequate flow turn down. And this is why it's critical to understand that turn down equation, because I have to be able to turn down properly on the chillers. Okay. The controls are a little bit more complex because I want to do feed forward control because that's the way this is going to work the best. But today, this has been around for a while now. This is not something that's brand new, cutting edge technology. It's been around for several years, and the controls are pretty well understood. Okay. So as I move forward, what I got to think about is, let's think about a real world scenario of what this means from an energy perspective. Okay. And we're going to look at primary, secondary versus variable primary. Okay. So this is a high school in St. Louis, Missouri, 1,000-ton chiller plant, 2 chillers, 500 tons apiece. And we're going to look at a couple of different designs. We're going to look at a 15-degree delta T design, and we're going to look at a 10-degree delta T design. And we're going to look at chiller turn down of 50%. Okay. So we're going to look at a step primary versus with a secondary, variable secondary versus variable primary flow. Okay. This is pumping energy alone. So if I look at variable primary with a constant speed secondary at a 10-degree delta T, my energy consumption for my pumps is 102,000 kilowatt hours. If I simply go to a 15-degree delta T, do nothing else, I'm still variable primary or constant primary, variable secondary, my energy consumption drops to 60,000 kilowatt hours just in pump energy. Okay. If I move to a 15-degree delta T, I now all of a sudden gain an additional 40,000 kilowatt hours in energy savings just by spreading the delta T out, because my pumps got smaller. Okay, my pump energy went down significantly. If I go to variable primary and do an all variable primary, get rid of the secondaries, now I'm down to 34,000 kilowatt hours in just pump energy by optimizing what I'm doing on the pumping side. That's an additional 25% in energy reduction. So as you look at this and understanding turn down and delta T, you can see why this makes so much more sense. Okay. At the end of the day, with the increased energy reduction and a 15-degree delta T, I really have the optimal system in energy efficiency and performance, and being able to cover a really wide range of load conditions. So part of the other thing that we got to think about, and we talk about pumping systems, we've got to understand, you know, for years and years we've done duty standby on pumps. The problem with duty standby is that duty standby only gives us so much turn down. I can only slow down a pump so far. And most of the time when I do a variable primary system, my chiller minimum flow rate is much lower than what the minimum flow rate is for the pumps. Okay. So if I look at turn down, what we're really looking at is the percentage of design flow at which the flow is stable and can still be accurately measured. So we got to understand that. So if I look at a typical pump curve, my MCSF value, or my minimum continuous stable flow, is 30% of flow at BEP. Okay. So on a typical duty standby application, I've got about 24% or 4-to-1 turn down, which means that, you know, I can only turn down that pump so far. Well, if my chiller minimum flow is lower than that, I got a problem because I can't turn the pump down any lower. Whereas if I look at putting 2 pumps in parallel, and you know, there's ways I can still provide redundancy because I can put 3 pumps in, each sized at 50%. Now I've still got N+1. But what happens is now I'm still 30% of BEP flow, but I'm 30% of BEP flow for a smaller pump. And what that means is that my turn down went from 4-to-1 to 8-to-1, which means I can handle that low end flow for my variable primary much better than I can if I'm just doing duty standby on the pumps. Okay, so hopefully everybody kind of understood what I was getting at there. It's all about accuracy and stability. Now, it wouldn't be fair to talk about a variable flow plant if we don't talk a little bit about heat rejection. And yes, I've actually been out looking at cooling towers in that kind of condition that is shown up on my screen right now. That's not fun looking at cooling towers when there's that much snow on the ground, because it's cold and miserable out there. Anyway, so when we look at cooling towers and we look at chillers, okay, let's all agree on one thing. The output of all 200-ton chillers should be the same. Okay, 200 tons, 12,000 BTUs per hour times 200. Chiller water side there, that's all the same. What we have to understand is on the cooling tower side, we have to be concerned about the gross heat rejection capacity that is required by the chiller. Okay, and that is entirely dependent on what kind of compressors you're using, what your chillers are. Okay, so the tower has to be sized for the gross heat rejection of the chiller. And the reason for that is we have the heat of compression in a refrigeration system. So we have to deal with that. Okay, I've done plants with steam turbine powered chillers. Okay, that changes all that because I've got other things to deal with on the steam turbine side. Okay, so I've got more heat rejection. It's not just the heat of compression. Okay, so if I look at the system, if I have your conventional electric drive centrifugal screw or scroll machine, my gross heat rejection is 15,000 BTUs per ton. Okay, so about 3 GPM per ton. Okay, that was kind of the baseline of what everybody sized cooling towers at. If I move to water source heat pumps, because yep, we put cooling towers on them all day long, I need 16 to 19,000 BTUs per ton. So a little bit higher rejection. Okay. Gas-fired absorbers, I'm at 22,000, a little over 22,000 BTUs per ton. And if I move to a steam-fired absorber or a steam-driven centrifugal, I'm all the way up to 30,000 BTUs per ton. Okay. The reason being is on a steam, especially on a steam turbine centrifugal, is I've got a surface condenser after the turbine to get the steam to condense back down into water. So I've got to reject that heat as well as the heat of compression off the chiller. Okay. So if I look at my cooling towers, if I'm going to control my cooling towers in a variable primary world, what I need to understand is there's some things you got to pay attention to. Okay. Normally in a design, we control a chiller plant. We have one chiller, one cooling tower, and that's the way we run them. The reality is, even when I'm running one chiller, I want to run water over all of my cooling tower cells. Okay. The reason for that is I can run all my fans at reduced speed because I got variable speed drives on all my fans, and it's going to consume less energy because it follows the affinity laws. Running multiple fans at lower speed is less energy consumed than one fan at full speed. Okay. Same energy, same affinity laws apply. So we can get better energy efficiency by running multiple fans instead of just one. Okay, so we got variable speed drives on all the fans. We want to modulate the fans in unison. So if you got 4 tower cells running, all 4 fans are going to run up and down at the same rate, at the same time. You're not going to have them stage at different speeds. They're all going to control to the same speed. Okay, the last thing is reset the condenser water set point based on the tower approach temperature. Okay, we know whatever your design is for tower approach, and we know what your entering wet bulb is. So if the outdoor wet bulb is lower than what the design wet bulb is, I can achieve a lower leaving water temperature because approach is approach. Okay, if I'm sized for a 7-degree approach on the cooling towers or an 8-degree approach on the cooling towers, what I've got to understand is that I can maintain that 8 degrees as we go below the outdoor wet bulb. So what happens is I can make cooler water. So when it's only 75, 80 degrees outside, I can make cooler water than I can when it's 95 degrees outside. But you've got to do it based on the tower approach. I've seen guys try to do this based on outdoor dry bulb. It does not work because cooling towers don't care about the dry bulb. They care about the outdoor wet bulb. So you have to base it on approach and the outdoor wet bulb to reset that tower water temperature down. And once you get it working right, it works beautifully. Okay. So, thing we have to understand with cooling towers. Cooling towers originally, a long time ago, way back when I had hair and it wasn't gray, cooling towers were designed for a specific set water flow, and they had the same amount of water flow over them all the time. Well, as we've moved away from that constant flow world and moved into the variable speed world, cooling towers have to be able to adapt to a variable flow rate, and not all towers can. So be very, very careful if you're going in and modernizing a chiller plant and you're not going to replace the cooling towers. Make sure you reach out to the tower manufacturer and find out what the flow rate turn down that tower can handle, because not all of them can handle it. Okay, so the way this works is when I have full flow, the tower manufacturers put these little things called cups in here. That's what these are. And what they do is they basically allow water, as we increase the flow rate on the tower, we fill that hot deck basin all the way up, and so it'll flow over the cups, and we cover all the media or all the fill in the tower. Okay. Well, as we slow the flow down, what happens is the water level drops below those cups. Okay, and so we start to not send water over the fill on the inboard side. So we're keeping the outboard side of the fill wet all the time so that it never dries out. And even that inboard fill is not going to dry out because it's got warm, moist air being pulled across it. Okay. And then what happens is we get even lower flow. We continue dropping down, and there may be staged cups, depends on who the manufacturer is. There's other different ways of doing this, but this is the most common that I've seen in looking at all the different tower manufacturers out there. This is the single most common way, is they put the little cups in there and change how much of the hot deck is actually active at any given point in time. So with that, this is how we're controlling the water flow rate and the level in that upper deck, okay, as we change the flow rates, okay? And in really low flow, no water flows over the cups. It's really that simple, okay? So I promised you what can go wrong. And one of the things that we talked about was, in a variable flow system, is understanding the minimum flow bypass control, okay? So first thing is, this is a real job. This is not made up. This job happened. On the drawings, this is the set of drawings. It's 2 package air-cooled chillers sitting outside in a chiller yard. Big note on the drawing says the PDH shall monitor the differential pressure across the evaporator barrel, and it'll calculate chill water flow. And when only one chiller is in operation, which would be the minimum load condition, the minimum flow bypass valve position shall modulate to maintain chilled water flow through the chiller above whatever the chiller manufacturer says is the minimum. That's all perfect. That is exactly what you want to have happen. There was another note on the drawing that said that there was a 3-inch variable primary bypass line with motorized valve. And so that's exactly what they did. Okay. What they provided, so a little bit of information. The chiller minimum flow is 90 GPM. Now, if we look 90 GPM to 3-inch pipe, not a whole lot of velocity there, not a whole lot of pressure drop, but that's okay. I can live with 3-inch pipe. So everybody understands the way.
Hey, Tony.
Yes, sir.
Heidi asked, I don't understand what the CT cups are to decrease flow. Are these manually fixed in place? Why not control flow with a valve?
So yes, I'm controlling flow at the plant level by reducing my speed on my pumps. What the cups are is so that as I reduce the flow rate, I have to keep the media or the fill inside the cooling tower wet on the air entering side, but I can allow it to dry out on the air leaving side. So that entire tower at 100% capacity, that water in that upper deck may be 6-8 inches deep. But as I start to reduce the flow rate, the water level in that upper deck could drop down to 2 or 3 inches. Well, I don't want to try to send that water over the entire fill because I'll get really poor performance and I'll eventually scale up the fill. And I won't get good water distribution over the fill because the fill really works by staying wet. And so what I'm going to do is I'm going to decrease the water level from the inboard side or the fan side of the fill because the water level is going to drop and not cascade over those cups.
10-4.
So we look at this variable primary chilled water plant, and hopefully everybody understands how to size control valves and understand that we size a control valve based on the C sub V. And so the C sub V is the value of, how much water will pass through that valve at a 1 PSI pressure drop. Okay, so for this particular 3-inch variable primary bypass line, the control valve has a C sub V of 320, which means that valve will pass 320 GPM at a 1 PSI drop. But the chiller has a minimum flow of 90 GPM. I think you guys can start to see where this is going, can't you? If I look at this, if I go down to minimum flow, the delta P across that valve is 0.1 PSI. That valve has no idea. It has no pressure drop. The water is the water, we haven't made intelligent water yet. So what happens is, as we try to go to minimum flow, the DP across that valve is so low, the water goes out right through the valve and right back to the chiller again. Well, the chiller's sitting there going, hey, wait a minute, my delta T is dropping like a rock. So it stages the compressors off, which means that the chilled water temperature starts to rise back up again. Out of the air handlers, because we're not getting adequate flow out there, because the minimum flow bypass valve is located outside at the chiller yard, what's happening is the air handler valves are driving wide open again. So the pump speed's going right back up again. And the pump's just constantly hunting. It can't figure out what it needs to do. The chiller's constantly hunting because it can't figure out what it needs to do. When you size that minimum flow control valve, that valve has to have a pressure drop somewhere in the 7 to 10 PSI range. Okay, we designed our system for a 10 PSI differential pressure at our most remote load, our hydraulically most remote load, or our critical zone, right? Well, if I got to maintain 10 pounds out there, I want that valve to have the same pressure drop so that the water doesn't have to make a decision whether it goes all the way out to the coil or whether it goes through that minimum flow bypass valve. I'm taking that decision of where the water is going to go away from the valve. Okay. I want the valve to have that authority, so it's got to have pressure drop. Okay. So this is one of those times that you really need to understand valve authority and understand how to select a control valve based on valve authority rather than just sheer pressure drop alone. Okay. Brett, we ought to do a class, we ought to do a Takeo Tuesday on control valve sizing in the commercial world and valve authority versus pressure drop.
Good idea.
Anyway, so to sum this whole thing up, so we have to understand the controls have to be able to compensate for flow change. And at a minimum, it needs to be able to handle a 10% per minute rate of change. Ideally, if I can get a 50% rate of change per minute control response, that's even better. And that's where, you know, high-end feed-forward control really starts to make sense. Okay. We know that evaporators in chillers have a minimum maximum flow. By the way, same thing applies to the condenser side. It's just not, it's a little bit different on the condenser side. You have to understand that those flow limits are carved in stone. You cannot violate those. So you have to properly design the bypass, and you have to know how much flow is going through that bypass. You really need to know that. Understand that turn down affects your energy savings. It also affects reliability and affects maintenance and a lot of other things. But you need to understand that a flow limit of less than 60% of the chiller's design flow rate, and also understand how to apply parallel pumping to that to get even better performance. Okay, pretty much by now, by code, we have to do 15-degree delta T, 12 to 15-degree delta T's as a minimum. The greater that delta T is, the better off you are. Okay, you've got to maintain minimum flow control, and you're either going to have a single modulating valve at the plant level, or you're going to have three-way valves out in the system. Okay, one of those two has to be there to maintain that minimum flow. It's up to you as the engineer to decide where that's got to be. I've done it both ways. It works both ways, and there are pluses and minuses to both. Okay, but you got to pay attention to that. You got to understand where you're going to put that minimum flow valve, and when you put it in the mechanical room or in the plant, you really got to pay attention to that valve sizing to make sure that the water doesn't short circuit. Okay, it's still going to go out to the system like it's supposed to. So with that being said, questions?
Yep. So Rand, a friend of ours from out west, wouldn't go back to your layout drawing, probably the last one you had there. That's when this question came up.
This one?
Yeah, I'm sure this is it. Wouldn't this layout risk having too little water volume when in bypass mode?
Yes, that created a whole nother problem, but that wasn't their, this job happened to be in Florida, so they didn't get down to minimum very often, but they did get down to minimum, and it created lots of problems. For this particular project, they trashed the pumps in the chillers in 3 months. Took the bearings out of them because the pumps never settled down. They were just constantly hunting up and down.
And here's another question. Instead of saying the pressure drop across the main, wait, let me start over. Instead of saying the pressure drop across the minimum flow bypass valve should be 7 to 10 PSI, is it more accurate to say the pressure drop across the minimum flow bypass valve should be equal to the control head of the system? That's a question and a half.
Yeah, I mean, there's two ways of looking at it, and I guess from my perspective, you don't want to go below the 7 to 10, but yes, you are right. It should be equal to the control head of your system, and understanding what that control head is.
And Nick is asking, when using three-way valves at air handlers, how do you typically specify which of the three ways provide the minimum flow? Is it good to have more than one provide minimum flow?
Yeah, and it's
Question.
Brett, it's really about understanding the piping layout. So if I have a building that's a fairly, let's use a hospital because they're typically a little more complex than a school is. And I've got multiple hydraulic zones out there. I may put a three-way valve in each hydraulic zone so that I've got constant flow out into that zone. Because the problem is if I put the minimum flow bypass in the mechanical room, what happens is I'm not getting flow out to my furthest, I may not be getting flow out to my furthest point out in the system. So, and I may also have to think about having a volume tank in there to have minimum system volume. I like having adequate three-way valves out in the system to meet that minimum flow requirement, and understanding, you know, looking at my chiller going, okay, I need to have 300 GPM minimum flow through that chiller at minimum load. Okay, now I just got to make sure I got enough three-way valves out there in, you know, out in conditioned world to equal that 300 GPM. Now, maybe it's a combination of a minimum flow bypass valve and three-way valves. It's all about looking at your piping and understanding your piping layout and what your building diversity is to make those decisions.
Awesome. And Henry's asking, ever put an auto flow valve in the bypass piping?
No, I'm not a big fan of auto flows, but that's me. I like manual balance valves, partly because I like what ASHRAE 90.1 says. ASHRAE 90.1 says thou shalt proportionally balance an hydronic system, and by proportionally balance, that means manual balance valves, in my world anyway.
Okay, so this diagram here, I think he meant to say HWP, but hello, in this diagram, what is HP-1 and why is it connected to the chiller? Is it a heat recovery chiller system?
No, so the chiller, you don't see the chiller pumps on this drawing. The HWP is those are heat recovery chillers, so that's why it's connected to the chillers. The chilled water pumps were provided by the chiller manufacturer, and they're under what's called undercoil pumps. So they sit inside the frame rails, and since they were provided with the chillers, they didn't show up on this drawing.
So this question's from kind of earlier in your presentation, and why do chiller manufacturers need why do chillers need minimum water volume?
So the problem is, think of it this way: you're a gallon of water, and you've just come out of the chiller, and you've been chilled down to 44 degrees or 42 degrees. It's all about how quick that gallon of water leaves the chiller, goes out, and comes back. So if I don't have enough volume in the system, that 1 gallon of water goes out, turns around, comes right back. My chilled water return temperature drops too quickly. And so you have to have minimum water volume so that the chiller has time to react, because I can't react in a split second. Even with highly reactive controls that can handle a high rate of change, you still have to have a minimum volume of water in that system to keep everything happy and to keep from short cycling your compressors. I can take you to a job here in Columbus that I know of that did not have sufficient volume. The chiller sat on the outside of the building, and they had 2 air handlers both sitting on the other side of the wall in the mechanical room. This was a 100-ton chiller. There was about 90 gallons of water in the system. The chiller would cycle off. It actually cycled off so bad it actually ate up 2 compressors in the first month of operation because the compressors were cycling so fast. So it's all about that cycle time.
I will say, you mentioned that a bunch of chiller manufacturers recommend or suggest 3 gallons per ton, right? I think you said.
Yep.
I would like to add the statement, please verify with the chiller that you're specifying or thinking of specifying.
Right.
I've learned that over the years, not everything's 100% in our industry. That's for sure.
Yes,
and
you're right, Brett. Every chiller manufacturer has a recommendation of what the minimum system volume is per ton of refrigeration. I've taken that, looking at the big guys, Carrier, Train, JCI, Daikin. I can't guarantee that every chiller manufacturer has the same requirement. That's just what I know from working with the big guys over the years, and that's where I pulled that number from. I know if you go back and look at the ASHRAE handbooks, there's recommendations in the ASHRAE handbook, and I think it's fairly similar to that. But you're right, got to look at what the manufacturer says.
So what is the rule of thumb for water volume per TR? It's 3. Oh, that's just.
Yeah, same thing. It's three.
Yeah.
It's 3 gallons. It's 3 gallons. The minimum system volume is 3 gallons of volume for every ton of refrigeration.
Yep. All right. So it is 1 o'clock. So we got a nice thank you and great job and pat you on the back. So you want to say something before I do my final sayonara, Mr. Tony?
Sure. Guys, thank you for your time and attention today. If you got more questions, you want to talk more about chill water plant design or control valves or anything, reach out to any of us at TACO. We're here to help. Thanks and have a great afternoon.
Thanks, Tony. Appreciate it. A lot of thank yous, a lot of pats on the backs. Somebody's asking for your email address. I'll make sure that Tony gets that statement and he gets it out there. A couple of statements. Heidi, thank you very much. Great question, and I love learning more about how to best set up controls. I'm sure you do. Get in touch with Tony. He's done it for many projects. Yes, Mohammed's asking if there's a recording. The webinar was recorded, and about 24 hours from now, you will get an email with the email that you registered with. It'll be sent to that email, I should say, and it'll have a link to that recording, as well as your PDH certificate if you would like. Okay, so just keep that in mind. And if there's ever an issue, just get in touch with us, and we have had to follow up with that in the past. So just keep that in mind. But other than that, let me see here. In 2 weeks from today, Tony's going to be back at it with another interesting TACO Tuesday, like all of our TACO Tuesdays are. Modern motor technology, technological differences from asynchronous to ECM and PMAC. I barely could get that out, but I know I've sat through it before. It's an interesting topic, to say the least. So thanks everybody, and we will be in touch, or we'll see you in a couple of weeks. Bye Tony, bye everybody. Thank you.
See y'all.